which is why we have invited two specialists. We have two presenters with me today, Robert Schillinger, Field Application Engineer at Wuerth Elektronik, eiSos, and Marcus Sonst, Application Engineer at Rohde and Schwarz. So hi Robert, how are you doing?
Hi Clemens, thank you, fine, very well. Outside we have a little bit snow, but everything is fine.
Okay, well, snow is better than the rain I have here. And Marcus, hi, how are you today?
Hello, hi. Yeah, I'm fine, thanks. Yeah, well, I'm looking forward to to do the presentation of this interesting topic.
Okay, well, but you will have to wait a bit because Robert starts, I think.
Yes.
Yeah, as we have quite some grounds to cover, I suggest that we start right away. I saw the presentations are quite long. So for all you who are attending, please note that this webinar is being recorded and will be posted on our Elektor TV YouTube channel afterwards. So you can watch it again later as many times as you like. Okay, so Robert, will you start?
Yes, I will start.
I forgot.
Sorry. Start with my top sheet. You know how to debug a flyback design is the content today. And what I will explain to you, I will show you some basics for better understanding how noise is coming from on this example, on the flyback example. And in the next step, I will show you how you can select useful components to reach the norm you must be handled. The only thing I show you today is by simulation, no real measurement. This is done by Marcus. He will show you something, how to measure it. I only show you the simulations. It's also possible to do EMC measurements by simulation. To start with the basics, I will show you a simple microstrip and both fields, the E field and H or B field, they coming together. I think that is a well-known thing. And the energy is transferred on or below the microstrip between the return path and the microstrip. Where both fields are close together. That's a main thing to understand the next slide I show you. I start on the left side with DC current. DC current will flow the blue line in the conductor to the device under test or to the load. And if you have DC, then the current will go back on the return path. And the return path you can think it as a complete plane, not as a single strip. It's a plane, a ground plane or a return plane. And therefore the current will flow on the lowest resistive way, and this is the red path, the red arrow, direct back to the source. If you have a little bit more frequency, starting at around 100 kilohertz and above, now the thing we see before will start to work. Both fields are coming together, and this results in the return current will flow directly under the outward current, because there is the best energy for both fields, and this is the reason why this is happens. The right picture, sometimes if you create a PCB, it happens that you split plans, or you break the original or the best return path. Like here, I print a slot below the outward current path, And then the return current must flow around this slot. And the whole loop you can see, the red loop, that's a kind of antenna and will radiate in the environment. That's a lot of times happens if you get radiated emissions by this reason. To understand what kind of filter is good for my design, I will show you both noise modes. Maybe you know the words differential mode and common mode, or it's the same like symmetrical voltage or current or asymmetrical voltage or current. A short explanation. On the left side, the conductor, the current will flow from the source to the load and come back on the right side in the right conductor where I2 is written. This is a classical differential mode current, like also the supply current, the DC supply current, for example. But we don't spoke about this current, we spoke about a noise current, which is caused by a switching mode power supply, for example. The other one starts also in the left conductor, go inside, and on the right side, I printed in the middle, also in the same direction from the load to from the source to the load. Also, this a current is flowing in the same direction, and to close a current loop, because if you have no loop, no current can flow. We need a back way for the current, for the sum of both currents, and this is the return path. It could be the earth, for example. It must not be a conductor. It can also couple by capacitive coupling to the earth and come back over the earth to the load. That's the both methods you can see in a design. And how I can differ it. The differential mode current, for example, is a typical current path like in the schematic. You can see in the schematic the same way. It's very easy to understand this path. And the return current is in most times very, very close to the forward current. And we spoke about relative high currents. And what we can do against this differential mode noise, we can filter with a simple LC or maybe a pi or a T topology. And the dominant reason is the current and the high change of the current, the high dI over dt is the dominant reason. I say especially dominant because sometimes or a lot of time you have both modes of noise. But you must find the dominant one. Maybe sometimes both are very, very high. And this differential mode results often in conducted EMI problems. On the other side, the common mode current, this path are sometimes unexpectedly. We have a lot of coupling and parasitic paths. The return path or return current path can be very, very big. We spoke about relatively low currents. Only some microamps are enough to get in trouble with common mode. What can you do against the common mode? You can filter with CMC, the common mode choke, and supported by Y-caps, for example. And the main reason or the dominant reason is a high du over dt. It's a very, very fast change of the voltage on the switch node, for example. And common mode results often in radiated EMI problems. Now I'll show you some path in an example, in a Flyback example. The red line, or the we have a lot of loops in principle, high di over dt loops in the outside path from the transformer via the diode, for example, and the output capacitor, or also on the primary side. Also there you have a lot of loops, of current loops. And this is one problem for inductive coupling and the usage of magnetic frame antennas you build inside such a design, for example. On the other side, we have the high du over dt voltages, a big voltage step caused by switching of the MOSFET. And for this, you get the common mode. And the flowing ways, for example, on the MOSFET side via the capacitor to the heatsink. And sometimes the heatsink is directly connected to earth, or also happens a coupling, capacitive coupling to earth, and then you close the feedback path. That's the common mode. For common mode, you don't need a real connection. It couples via capacitors or parasitic capacitances. Now we come to the example we will present from my side in a simulation, and from Marcus' side on measurement equipment. And the listen we show in the or on the web, and also in the articles. And I say something about the Flyback. We have typically 24 voltage input. We have 5 volt output at 5 amps, around 25 watts. We using the chip with 300 kilohertz switching frequency. You can see after a few slides this frequency again. And we reach an efficiency of around 90%. To use LT Spice as a simulation tool without any cost, you can download from Analog Device page. We use also an IC from Analog Device to have an easy simulation. And this is a synchronous rectifier on the secondary side. As transformer, we use one from Wuerth Elektronik, and the MOSFET is in a TO220 package. That's the facts, and now we start some calculations. For example, if you have an efficiency of 90% and I add additional safety margin of 10%, we can calculate from the output power back to the input power. And in this way, we can to maximum input current. We can see in the second line, in the worst case, we have at 19 volt input voltage around 1.65 amps. That will be important a little bit later, but I show you here to remember. Okay, as I tell, this is the result of a simulation. Also, the last picture or the last, the last slide I will show you is also a simulation, and but it fits very, very well to a real measurement. That's the fact. You can see it in the second presentation. What we can see here, the 300 kilohertz as the first peak, up to 70 dB microvolt. It's the average value, and the average class B borderline for this would be at around 50 dB microvolt. To have a good solution, we say every time try to be 10 dB below the average line. And this results in around 30 dB, what we must have an attenuation device to filter the differential mode. That this is a differential mode. You can see at the 300 kilohertz base frequency and the harmonics at 600, 900, 1200, and so on. Every 300 kilohertz, you get a peak, and you must do anything against this differential mode noise. At the end of the diagram, around 10 megahertz, you can see typical common mode noise overshoot. It's a wideband, and this is the second one. And on this design, on a galvanic isolated design, you have very often both noises together, relative with the same amount of noise. Okay, to start, to select the correct component, I will start with the common mode choke to try to reduce the common mode noise around 10 megahertz. And how we can select such a component, we have a lot of possibilities. And for this, I will use the worst case input current I calculate a few slides before. Then I try to reduce the size of the component to a minimum. Often you have no space in your design. I must use the correct material for the correct frequency it's frequency dependent. To reduce the noise, you must know the frequency and the corresponding material. And at the end, you have a look on the impedance curve of the component, and this should be fits to your noise. You should have a very high impedance or a high attenuation at around 10 megahertz. That's the important thing. What we have online is the Red Expert tool. You can see here a picture of it. And this tool you can use to easy filter to this parameters I show you. Yeah, I do this step by step. We have the 1.65 amps maximum. For this, I will start at this current, 1.65. And to get not so much fits, I border it at 3 amps. Because you can have also a 10 amp, 16 amp component, but this will result in very big sizes. It's not so nice. To set the correct impedance, I use a filter tool. The slide you can see in the right picture, in the below picture, and I set it to around to a minimum value of 25 dB. Because I have a look on the reference measurement or simulation in this case, and fit this to 25 dB. To get a small component, I set only S components, also S for small, so enough for the current, but not so big component. Yeah, at the end, I get in sum 5 parts which will fit to my needs. And now I will show you 3 parts of the 5 which we can in principle or which are in principle selectable. We have the blue one, that's a nanocrystalline material. We have the yellow one, that's a manganese zinc component. And we have the green line, which comes from a nickel zinc component. Because of some experience, I will select the yellow one. And at the end of the presentation, I think you will know why I do this. But now I say I use the yellow one. The next part will be to do anything against the differential mode, and for this a simple SC filter will be enough. You can calculate this by the reading of the simulation diagram. If you remember, we had at 300 kilohertz, or we need at 300 kilohertz around 30 dB. And the LC filter is calculated by the formula you can see here. FC is the corner frequency of the LC filter. And I set the corner frequency, it's a rule of thumb, 1/10 of the switching frequency. In this case, to around 30 kilohertz. Then I can put, for example, a C value if I have on my desk, and calculate with this formula the L. Or if I have a L, then I can do the same vice versa and calculate the C value. That's in your hand how you do it. I start with these values, 10 micro inductor and 4.7 microfarad for the capacitor, and I do all, or I put all in the LT Spice simulation, and get at 300 kilohertz. You can see in the picture the gray cross. It's put on 300 kilohertz, and I get more than 40 dB attenuation. That's very nice to reduce the peak we saw in the simulation. Now I start a little trick to remove the discrete LC filter and use only a CMC in this case, because every common mode choke brings you a so-called stray inductance. And if you use this stray inductance together with a kind of X2 capacitor, or capacitor in this case, then you can build a similar LC filter, but without inserting an extra inductor. And this works with my selection very well, because I can measure at the differential mode diagram. You can see here on the left side. That's the differential mode impedance of the common mode choke. And with these calculations, I can read the at 300 kilohertz the impedance, and calculate back to the inductance. And if I do this with this formula, I see I have around 10 microhenry. And if you remember, I use also a 10 microhenry inductor for the LC filter. And this is the trick. With this 10 microhenry, I only use an additional capacitor around 3 microfarad. And I select in the example of 4.7 microfarad capacitor, and for this I get a corner frequency of around 23 kilohertz, and that's far enough from the 300 to get a very, very high attenuation at 300 kilohertz. And in this way we can compare both. The black one is with an extra component, an extra inductor with 10 microhenry, and 7.4 microfarad capacitor. And you see, if I use the common mode choke in the differential mode, in a differential mode way, and combine it with also a 4.7 microfarad capacitor, then I get nearly the same result. And for this, I can use the stray inductance of the common mode choke in this case. If I put into the design and start the simulation again, I will get very, very low noise. I drop down every peak I see on the 300 kilohertz, the green line. It goes only to around 30 dB microvolt, and the rest is completely damped by the filter structure. It's not completely the complete truth, because in simulation I get no basic noise. If you run such a system with measurement equipment, you always see around 10 to 20 dB microvolt kind of basic noise. That's not possible in the simulation. But I think you can see the basic principle, how you can reduce any noise from such a system. And that's, I think, is the important thing today. Back to the article and the project, what is behind this webinar. I put it here, an QR code to get a direct link to the Elektor shop. Also the same you can see above is the link to the Elektor shop, is a short link from our side, but you come to the Elektor shop and where you can buy the DC Listen to debug your own DC components, switch mode power supplies, or other devices up to 60 volts. Okay, that's from my side. I thank you very much to attend to this webinar. I give now to Marcus and he can show you some measurements with this equipment. And after his presentation, you can ask a lot of questions if you like. Thank you, and have a nice time.
Okay, yes, thank you, Robert, for this presentation. Just one quick question. People are asking if your LT-SPICE simulations will be available for download.
Not at the moment, but I think we can do this.
Yeah, we could add them to the product page, for instance. And just to let you participants know that the Listen is already sold out, but a new batch is coming up and should be available in 2 weeks, I was told. So please have a little patience. Okay, then we move on to Marcus, who is going to use oscilloscopes.
Okay, thank you, Clemens. Let's start with my topic, debugging conducted emissions with oscilloscope. So it's more the how to measure that noise, especially with oscilloscope. So these are the objectives of my presentation. It's divided basically in 2 parts. First is more the general topic, EMI debugging with oscilloscopes, the performance levels of instrumentation, the EMI debugging, especially with the oscilloscope and its limitations. There are, of course, some limitations. The tips and tricks I would give you, that is quite important, I think, when we are talking about this topic. And I would like to present you also an Emi Debug Tool, which enhances the oscilloscope to a more valuable tool in the end. And the second part is all about common mode, differential mode separation. I will present you the case study and some conclusion in the end. So let's start with the performance level of instrumentation. We actually divide these performance levels in 3 parts. The third level is basically when we are talking about full compliance measurement. And that is basically the field of the dedicated field of EMI test receivers, because they are very precise and accurate in terms of this, and it's full compliance. The people in the test houses are using those equipment typically. The second level is basically when we are talking about pre-compliance, so everything which differs from the compliance measurement is also covered by EMI test receivers. with lower classes instruments, and at the same time it can be also performed with some top class spectrum analyzers and also some general purpose spectrum analyzer with some additional options. And the first level, the lowest level, basically, it's when we are talking about diagnostic measurements in the lab, and that is the dedicated field of low-cost spectrum analyzer, and also oscilloscopes, the high-performance oscilloscope, but also low-cost oscilloscopes. The instrument classes, so the EMI receiver and spectrum analyzer and the oscilloscope, differ in terms of how they measure, basically. So the oscilloscope is a device where we measure really at full bandwidth, so it's a wideband measurement device. On the compared to that, the EMI test receiver or spectrum analyzer, they measure really with a smaller bandwidth, and they're sweeping through the whole spectrum. And that's why the EMI test receiver and the spectrum analyzer are so good in dynamic and sensitivity. Furthermore, they provide some nice features like logarithmic scales and limit lines, and yeah. On the other hand, the oscilloscope is very good to be fast and yeah. Especially the time frequency correlation is easily possible with an oscilloscope. It's also possible with the other classes, but it's always an additional option, and you are coming from a different perspective. And yeah, we suggest actually for EMI debugging, the oscilloscope is the right choice. Why is it the case? Well, when we are talking about EMI debugging with oscilloscope, yeah, it's already, the oscilloscope is basically already on your desk because you're developing products, and for that, of course, you need an oscilloscope. And nowadays, the oscilloscope are so good that they have already an FFT capability usually, and yeah, there you can really test your improvements or changes very fast. And yeah, as I said already, correlation between time and frequency domain is very interesting with the oscilloscope. And also the triggering can be enhanced. For example, of course, triggering on time in the time domain is still possible, but with some oscilloscope models, it's also possible that you trigger on frequency events, especially on the high value instruments and the high performance instruments. And last but not least, the user interface is nowadays very good. So it's similar to a spectrum analyzer: start frequency, stop frequency, resolution, bandwidth, that can be easily defined. And just to give you an idea, so we have here 1 millivolt per division in vertical scale on an oscilloscope, and this corresponds to a displayed average noise level, which is a typical value for a spectrum analyzer to tell you how much noise is in the system. So 0 dB microvolt is basically what you can expect from an oscilloscope. Okay, what can we do with the oscilloscope specifically? So we have, as I said, a high performance oscilloscope here, our RT06, but we also have these RTB 2000 low cost oscilloscope, basically. And this is also the focus of today's presentation here. We are talking about with this oscilloscope class. So we have basically two fields, what we can do with an oscilloscope. One field is the near field probing, and that is especially valuable when you have a far field measurement from a test house, for example, and then you can use these near field probes to isolate your noise source, basically, on your PCB. So what you are doing here is basically you are measuring currents and also electrical fields and magnetic fields with a certain distance, and then you can really locate the EMI noise. For the conducted emission topic, we need a different accessory that is the artificial mains network or line impedance stabilization network, and you need either an AC type or these DC type line impedance stabilization network. And that's basically what you need in your lab or R&D lab to perform EMI debugging. How does it look like? The basic EMI conducted emission, it's similar to what the standard is defining, but yeah, reduced setup, I would say. What we have here again is the instrument, the oscilloscope or spectrum analyzer. We have the power supply unit to supply your DUT. We have, of course, the DUT, which was the flyback in this case. And of course, in the center, we have the line impedance stabilization network, which is used for several purposes. And one is to create a defined impedance for the DUT here to be comparable with the measurement results. It also creates a high frequency coupling path for the instrument. And the third topic is basically, or purpose is to filter any noise coming from the power supply unit. Could be also the AC grid, and we don't want to measure that noise. We want to measure the noise from the DUT. So we need some kind of filtering there. And in that, addition to that, we need also this light blue reference plane, which is a ground plane, to provide also a current path for the common mode. It was already in Robert's presentation that it is important to have a current path here. But that's basically all what you need for EMI conducted emission measurements. So how does it look in real life? That was my setup. Hopefully you can identify the instruments. So this is my RTB oscilloscope I used. On top of the picture here is the power supply unit, the listen, the DC listen, the ground reference plane, which was a copper plane, and this device in the back was used as electronic load because I had to use somehow an electronic load for the flyback DUT here in the middle. And there are also some boxes on the ground plane, which I will describe later on what is the purpose of that box, those boxes. But that's actually a quite common setup, I think, in the lab. So now we are coming to the tips and tricks section. I think very important. There are possible impacts which can influence your measurements, especially when you are performing those measurements in your lab. So typically, we still have FM transmitter for radio, for example, and those are everywhere. And it could really happen that you create a setup with where you have some antenna due to the cabling, where you really measure or receive these kind of magnitudes. So especially this 80 up to 108 megahertz range is quite common, that what you see in the spectrum. And therefore, it's always recommended that you do a measurement without the DUT switched on, and to get an idea what is your environment, how does it look like, what kind of emissions do I have to expect. Later on, when the DUT is switched on, this is an important information. More difficult is basically these effects can also be temporarily visible. Good example is, for example, is if your colleague is switching some high currents, some high DIDT, it can be easily transferred to radiated emissions, and this could also infect or impact your noise. And this is only temporarily available, so that this is more important, or more difficult to overcome this problem. But that happens in an open lab condition, and the message is basically you are not in an shielded chamber, and that's why you have always consider some emissions in your setup can be caused by other sources. So the cabling is, I mentioned already, it is critical, and especially when you're using very long cable, you can create easily quite good antennas to receive any RF noise which is in the environment. So recommendation is to keep the cables as short as possible. It's always a good advice. Also, the sampling rate of digital scopes is an interesting topic, and it cannot be infinite, of course. And you can easily get into the problem with the Nyquist criterion when you have really high frequencies somehow from the external environment, and that could produce basically a aliasing effect. So keep an eye on the sampling rate, that it is sufficient enough and high enough. One idea is to overcome this problem is basically to use an analog filter. So there is typically the 20 megahertz filter at the oscilloscope input, and of course this can reduce this effect. But the problem is, of course, if you want to measure up to 30 megahertz according to the standard, it doesn't work for sure. Of course, also the high bandwidth, if you have a 1 gigahertz oscilloscope, you have to keep in mind that you are able to receive any noise up to 1 gigahertz, basically, because it's a wideband measurement device. And these coax cable system, if you are using two coax cables to measure 2 channels, that comes later with the common mode differential mode separation topic, there should always be or should have the same length, because otherwise we have some skew effects that we'll show you later on with some measurements. And I mentioned already there's boxes on my reference plane, the black and white boxes, and that was basically to create a distance between the reference plane and the cabling. And this is basically a capacitor, what you are defining there. And as Robert already mentioned, common mode is not that high, and in a high frequency range, that really matters, that you have a constant distance between the power lines and the reference plane. This is really important to have comparable measurement results. So this is the skew effect I mentioned already. I did a good measurement on the left with the same BNC cable length, when there is no delay between channel 1 and channel 3, almost no, some picoseconds. And then I introduced a 26 centimeter BNC cable on channel 3, and in the end I had a delay of almost 2.5 nanoseconds. And if you imagine that when you do some calculation with channel 2 and channel 1 and channel 3, of course, power can be multiplied, for example, voltage and current, then you end up with wrong measurements, basically. So cable length is really important and should be always the same. Then we have the input impedance of the instrument. Typically, the RTB, or at least our RTB, only provides 1 mega ohm input resistors. Some higher or more expensive devices also provide internally a 50 ohm resistor. And that is helpful when you want to have a nice impedance matching, because a line impedance stabilization network requires a 50 ohm adaptation. So we have only the 1 mega ohm on our RTB. What to do is basically, or at least we can make it better when we add an additional external 50 ohm resistor to have a better impedance matching. And that matters, of course, only at higher frequencies. So when we are talking about higher than 30 megahertz, would be better to use this 50 ohm to have no reflections, or even if your scope provides an internal 50 ohm, then of course use that one. Some words about the noise we have here. That was the measurement with the RTB I did. So the top is the time domain, what you can see there, and the bottom is the frequency domain measurement, where we have basically an optimized noise floor with the instrument. So nothing was connected. The lowest vertical scale, 1 millivolt per division. And also enabled the high resolution mode to get this 16-bit quantization mode. which also ensures that we have really less noise. So the best what we can get, and we had a noise floor of minus 10 dB microvolt. The next thing what I did was I disabled the high resolution mode just to give you an idea what does it mean in terms of noise floor. So you see it already in the time domain, but it's easier to measure here in the see it here in the frequency domain, and we are talking about now at minus 1 dB microvolt. So it was just the high resolution mode disabled, and we have we have now the 10-bit quantization, which is the normal operation sample mode. But that introduced already some noise effects. And the problem is now here we have still the vertical scale of 1 millivolt per division, which is not very practical. When you want to measure conducted emissions, you of course have some magnitudes here in the time domain, some amplitudes. So you have to increase usually your vertical scale to a higher value to avoid clipping. And to show you that effect is basically here. So I did some analyzation of the amplitudes, and I had to choose the vertical scale of 50 millivolt per division. I again enabled the high resolution mode to have lower noise. And the result was basically that I had a noise floor of 8 dB microvolt. DUT is still switched off at this measurement. It was at this measurement. And this is a more practical value. So 8 dB microvolt is basically what you can expect when you have a reasonable vertical scale. However, the message is you have to analyze your vertical scale before you do your conducted emission setup. Otherwise, if in case you have some clipping, so overdriving the A to D converter input, this red end arrow indicates that you won't get reliable measurements, and also you have to use the full scale of your vertical range as much as possible. This is always to have proper measurements. Yeah, right. So in the end, I switched on the DUT, and this what was the measurement I got. On the left, I measured on the positive conductor, and on the right, I measured on the negative conductor. And well, it's a measurement, and it's fully correct, but it's very hard and not convenient to analyze, I would say, because especially here the lower frequencies are very dense nearby, and this is also and it seems that it's also the same on the positive and on the negative, and so it's not so convenient, I think. And therefore we introduced the Emi Debug Tool, which is an external PC tool where we really have nice extended features in combination with the oscilloscope. So for example, it improves the usability. It's easier to define all the settings on the oscilloscope for the FFT with focus on EMI, of course. It provides limit lines. You have maybe noticed on the previous slide there were no limit lines, and here we have now limit lines according to whatever standard you would like to have. They are freely definable, and we have now also the logarithmic scale on the x-axis, on the frequency axis, and that's why it's much more convenient, because you can see here the 300 kilohertz switching frequency, and it wasn't so easy on the oscilloscope itself. And of course, it provides data export for further analysis. And this is what I would like to show you in the video, which we will start in a few seconds. Yeah. How does it look like? So this is basically the start window, and what we can do here, we can select and define on the right the start frequency, stop frequency, all the frequency settings where we need for our conducted emission setup, the vertical scale, high decimation, and in addition, we can also define or select the limit lines in the left bottom corner. according to the standard we are using. And we can have 2 FFT traces, one for peak and one for average, which is also quite convenient and common to use that on oscilloscope. And now we are changing to the instrument view, because I sent now the data to the instrument, and this is the startup default setup of the oscilloscope. And now the setup gets transferred, and you see a lot of events happening on the oscilloscope. And in the end, here we have now our spectrum, our emissions. We only have now to transfer from the instrument back to the external PC tool. And it's still the same here on the oscilloscope window. It's not so nicely shown, because mainly due to the missing logarithmic scale. And now we are switching back with the camera to the external PC tool in a few seconds. Yes, now we are switching back. And the only thing what we then have to do is just ask for the data. So we have to press only one button and ask for the data. The limit lines are already in the main window, and it takes a short moment, depends on how fast the transfer can be, or the link you have used. And here now we have our spectrum, and of course we are exceeding the limits at the moment because there were no filter used in this setup. So I think that was the demo from the Emi Debug Tool. And now we are coming back to the presentation. Well, I think I have to go through quickly. Okay, the question is now, okay, we have done our measurement with a better view now, but the question is, how can we distinguish between common mode and differential mode? Because we have learned recently that it is quite interesting to know that. And when I measure just in the normal procedure according to the standard, I don't have that much more information, and therefore we have derived some equations, or others did it already. I don't want to go into the detail. Robert also described it a bit. The only message what I would give you here is we are using some math here on the right. Vp and Vn is a measurement on the positive, voltage measurement on the positive conductor and on the negative conductor against the reference ground. And by that, and applying some math, we can derive the common mode noise and the differential mode noise. It's also described a bit more in depth in my application note, which I will paste the links later in the chat. But this is the related application note, and by that, we can distinguish between common mode and differential mode, and that is a great thing when you want to define or to develop your EMI filter. Right. So we have basically different solutions for that, or there are some solutions around. One is a hardware solution to separate these noise by basically using these kind of math. And this is the circuit here. We are using here, or they're using the wideband transformer to separate the noise portions from the VPN VN to the common mode noise, and the other way to the differential mode noise. And then we can measure with a one-channel device like a spectrum analyzer, but in this case it's an oscilloscope. They have typically more channels. But anyway, this is the method where you don't need any software, external software, whatever. And this was the design which I will later on, also from Wuerth Elektronik, I will later on use in my case study. The second solution we propose, or we suggest, is basically when you're using these high performance RTO6 class instrument, which is an oscilloscope where you have the capability of multi-channel FFTs, you really can do the math, this addition and subtraction math directly on the instrument, because the hardware is powerful enough, and it's also, the screen is big, and it's really convenient to use that scope with these kind of software solution. But the focus, as I said already, is the RGB 2000 today for a lower budget. And therefore, it's not easily possible. We don't have these multi-channel FFT capability on that scope. And therefore, I had to write a Python script where I do a setting at the beginning. Then I'm measuring on channel 1 and channel 2, do calculation on the instrument to obtain the differential mode spectrum. The next step is then to use or to repeat a measurement on channel 1 and 2 and do again a calculation with the math. But in this case, it's a common mode spectrum. And then I'm showing the common mode and differential mode also with Python, because there I can also easily show it in a logarithmic way. And that is quite convenient, what we saw. And yeah, this is what I eventually did. So I used the RTB 2000 in combination with a Python script and did a kind of case study. So I started with this flyback converter. I started basically without any filtering at the input. So we're talking about the worst case in this measurement here. No common mode and differential mode filter. And what you can see here is basically on the left as a software solution 2, where we have in the top window the differential modes spectrum, and in the bottom the common mode spectrum. So yeah, quite high at the moment because we don't have a filter. But anyway, I did the same measurement, same setup, common mode, differential mode filter setup, and I used in this case here on the right the hardware solution, what I've shown you on the previous slides. And what I would like to show you is basically that the results are very comparable. So they are below 5 dB microvolt. It's hard to read, I think, on these slides. But if you compare the signatures itself, it's really a good match, I think. Also, it's either on the differential mode, but also on the common mode. As a next step, I applied Y capacitors to filter the common mode noise. And this is really what you see in the bottom of this slide here in the 2 windows. The common mode is really attenuated a lot, especially here at higher frequencies. There are some smaller deviations here with the hardware solution, but yeah, this is still in the 5 dB microvolt region. So I think it's quite reasonable to have those measurements. On the differential mode, it's almost the same because we haven't attenuated the differential mode noise. So then that is basically the last step. I enabled the X capacitor, which is relevant for differential mode filter. And you really see here the great attenuation here in the differential mode on the left and also on the right. So it's really damped. Only the switching frequency at 300 kilohertz is a bit still visible, but all the rest is really nicely filtered. And also the common mode is almost the same. Right, so coming now to the conclusion. So I think the oscilloscope is really a good and great tool to debug EMI, especially in the lab. And you can really easy and fast optimize your application. Second topic I would like to mention or to highlight is really that you have to keep an eye on the setup, because that is always a bit critical and you don't know the environment. And that's why you have to consider these relevant effects. And if you do that, I think that is a good method to to optimize your development. And last but not least, the external tools I showed you, I think they can really enhance the oscilloscope in a powerful EMI debugging system. And yeah, I think that is quite helpful. And in this sense, I would like to thank you. I hope you enjoyed my presentation, and I'm waiting for your questions.
Okay, thank you, Marcus. That was very interesting indeed. We have also some questions, so I will move to switch to Q&R mode. So, well, we start with the easy ones. Will the slide deck, the presentation, be available for download? I think we can do that. I don't think there is any top secret material in there that Wuerth or Rohde do not want to diverge. I mean, it was already in this webinar recorded, so that's no problem. Then we have a question: how to connect a DC-DC power converter to a listen? Maybe Robert can answer that one.
Yeah, I think this question come at my presentation, but maybe it's answered by Marcus' presentation. If it's because he shows some slides where you can see how to connect the DC-DC power. In principle, yeah, you put the listen between your power supply. Yes, this I think is a good solution. On the left, you have the power supply. Then the listen is coming. You put plus and minus on the left, and the device under test on the right side, also plus and minus. And yeah, the oscilloscope directly on both channels and use the mathematic functions, or you also can add a separator or a combiner. I don't know what is the best name for this device. You have a lot of solutions for this, and yeah, important thing I think it's also shown by Marcus is that you have a conducted plan below the whole system.
Yeah, we have a good.
Yes, that's correct. You see the copper plan and the device under test, the cabling, and also the listen is put on this conducted desk to have a possibility to couple, or the common mode can couple to this plan. That's the important thing. And on the back side of the listen, maybe you can see between plus and minus, there is the earth connection, and also the case is a metal case, and the measurement PCB inside the listen is connected to the metal piece. And if you put the metal piece on the copper plan, then you have also a connection. You can do it by a cable, or to put the listen on the conducted plan. And that's, I think, the most important things to have good solutions for measuring differential and common mode, especially the common mode.
Yeah. So here, normally you see a pointer. I put a pointer, activated a pointer. No, on this.
I searched for the pointer.
No, I thought I had one, but
I don't know. But
yeah, here on the left, you can see these blocks that you mentioned to make sure that the cables are at the right height. And here we have the BNC cables on the right that must be on the same same length.
Yeah. Yeah. If the question is not right answered, feel free to contact us directly behind this session tomorrow or next week. If you need any explanation, then I think we can do this.
Okay. And this one we already answered quickly, so we will try to do this, huh?
Yeah, we can do. I have a model for an LT Spice model for the listen, for the dual listen in this case, and I can send also the example of the Flyback. It's not a problem.
Okay.
It's not a secret.
Okay, this one refers to slide 13.
Yes, it's a good question because I print the differential mode and common mode noise. Because of experience, and I can split, or I take a lot of measurements and I split, and I know where common mode noise and differential mode noise is happen. And also on slides from Markus, you could see the same things on the measurement. He shows at the last slides both measurements, differential mode, common mode, and I think you can see it very, very nice. Where is the common mode and where's the differential mode? And in principle, you measure in the laboratory both together, and you can't see the difference. You have both, and the compliance test shows not only the differential mode or common mode, it's always both together. But to debug and to find the correct solution for a filter, you must know what kind of noise you have. And that is only possible if you split it in two parts. But here you are right, I have the experience, and for this I can say here is common mode and there is differential mode.
Okay, thank you.
Hope this is enough.
Another question, this one for Markus, I think. Can I use the Emi Debug Tool with the RTH 1004?
With the RTH, I'm not sure, but of course we have other scopes, the RTM and RTA, where we have this Emi Debug Tool, and then there's also we have it's called a pre-compliance tool. We have also this kind of tool for the RTO class and RTE class. For the handheld, I'm not pretty sure, to be honest, if that works, because that is, it was not the focus of my my work in this sense. Yeah.
I have a related question. Where can we find the Emi Debug softwares?
I have already prepared the links. I just have to paste them in the chat window. So there are a link where you can really can easily download this Emi Debug Tool. Yeah. So yes. I can already do that.
Then we have another important question. Where can we buy the hardware Cmdm splitter, the listen? Well, you can buy it at Elektor. The link is already in the chat, I saw. I can paste it again. I had prepared it also. Here we go. So it's now in the chat box. You can find it at the Elektor store. If you look for listen, you will find it immediately. Please note that the first batch is already sold out, and the second batch is coming, and we hope to have them within 2 weeks. So please have a little patience. Then we go to Python. Will the Python scripts be available?
It's at the moment it's just a prototype, and we are still in discussion. The basic idea is basically that we implement these kind of Python into the Emi Debug Tool, because at the moment the Emi Debug Tool is only able to use one channel at the same time, and we need just to incorporate these Python method into the Emi Debug Tool, and we think that is a more convenient way to have it. But in case, so at the moment it's not available, but in case it won't be in the Emi Debug Tool, then we will of course offer this also as download. But it's not the case right now.
Okay. Then we have a short question: XY capacitor. Who wants to answer that one?
Who should answer? I have no nice picture to show what is X and what is Y. Can I draw?
Yeah, you can draw on the. Should be able to draw on the.
Ah, okay. Whiteboard, okay. Now I search for the drawing tools.
They're below. You have these colored squares below in the circle.
No.
You have to select from the.
No, I have no
There's
drawing tool.
a pointer, an arrow icon, and there you can select a pen.
Ah, okay. Yeah. Now I have found. Thank you. Okay. If we put here the plus, for example, and the minus, or in brackets L1 and N, you have here this capacitor is known as CX, and if you put here a capacitor and here in this way, put this to earth, then you have here the CY and the second CY. That's a difference. And if you use common mode choke between there, then you have here the X plus the stray inductance of the common mode for the differential mode distortion or noise, and the Y caps you use it together with the common mode inductance of the CMC to attenuate the common mode noise. It's a combination to get a second order filter in principle, and that's different. This is Y and this is X.
Okay. Thank you, Robert. You are very good with the mouse pointer to draw things.
Thank you.
So I hope that answers your question about XY capacitors. Let me see, what else do we have? It's just, this window is just too small. A three-phase listen.
Yeah, that is probably, I could try at least to answer. Yes, a three-phase listen with one RF output exists, and I think we have it in our portfolio. And this is really a device where you only can perform these pre-compliance and compliance measurement. So you cannot split the noise because you're not measuring. You cannot measure on channel 1, channel 2, and channel 3. We don't have a listen for that. And with one RF port, it's not possible. But what you can do is basically you can use current probes, and with the right wiring through the current transformers, you can basically also do the same. So you have either the common mode or the differential mode. But that is then you are measuring microamp dB microamp, and then you have to transfer it to the micro volts again. But yeah, that is a way typically the people do it with the current transformer. I hope that that answers your question.
Okay, I don't know, but we move on to the next question. Why did you design the CMC considering the measurement up to 30 megahertz?
Yeah, because for Flyback especially, in this case low voltage Flyback, the same happens at mains Flyback, but in this case for the low voltage, you get always, because of the galvanic isolation from primary to secondary side, you get always a common mode noise in the area of around 10, 20 megahertz. And that's the reason why we use a common mode with manganese zinc here. If you have also trouble in the radiated, then you can add a second one, or also a snap ferrite, for example, on the direct on the cable to use the high frequency part of a common mode. But that's a way. You use a two-stage filter, one with a low frequency common mode, and the second one with the high frequency one. That's a possibility. Or you can add on the cable a ferrite. It could be a snap ferrite or a ferrite ring, such kind of ferrite. Then you can reduce also the range from 30 megahertz to 1 gigahertz if you have trouble in this range. But as you can see, you have also in the low frequency area trouble with common mode, not only in the high frequency. And that's a typical thing of Flyback.
Okay, thank you. Then we already answered this one. We can answer it again with yes. Huh?
It does, yeah.
Okay, so apparently we didn't answer a question right. This was about how to connect it. It is not the listen, but the Cmdm splitter. Did we have a slide for that?
I think that was the same slide we showed already.
Yeah.
Where we had this separation.
Where I'm scrolling through the slides.
Yeah, this one.
Yeah.
So there is the noise separator basically. And yeah, you have to connect the positive and the negative between the listen and the noise separator. And on the other end, there's either the common mode or the differential mode connection.
Yeah.
That's it, basically.
Okay, people ask where to get the Dcmdm splitter. We don't have one, as far as I know. But...
Yeah, there are different possibilities. I think we write the parts from mini circuits to your homepage and the link to that.
Okay.
You can buy such a splitter. This one on the picture you can see is additional board from my side. I have also a colleague from France. He create also a combiner splitter with other parts. If you have interest in the schematic in the production data, you can connect me and I can send you. It's not so hard to create the PCB, and on the PCB they are using two common mode chokes from us and SMA connectors. It's also a possibility.
Okay, maybe
we can also add this small project to the listen at the Elektor page. It's okay from my side. I have no problem with that.
Okay. So I guess we should stop here now. I just quickly want to show one slide that I forgot to show in the beginning, so that we know who you were actually. Thank you for being with us, Robert and Marcus. Oh, sorry, it's not. Yes, no, it's on. And then we go to the end of the presentation, which is here. Okay, well, thank you all for watching this Elektor webinar. As said before, it has been recorded and we will publish it on our Elektor TV YouTube channel. The Listen device can be found in the Elektor shop as soon as it is back in stock. I would like to thank Robert Schillinger from Wuerth and Robert Marcus Sonst, sorry, from Rohde and Schwarz for doing this webinar with me. And of course, thank you, audience, for being with us and asking good questions. Thank you, goodbye, and I hope to see you for our next webinar.
Thank you.
Thank you and goodbye.
Yeah, bye.